So now we'll do this question. In this question, let me first explain the question. There is this wooden block and there is this spring of spring constant K. The wooden block is having the dimension of 3 centimeter. Each side is of 3 centimeter dimension, and the density of this wooden block is 800 kg per meter cube. That's the density. So this wooden block is floating in water. This is water. The density of water is 1000 kg per meter cube. It is floating there. And there is this spring. This spring is not connected with this wooden block. It's just touching it. So basically, when the wooden block is floating, at that time, this spring is just touching it. So it is in the natural state, natural length. This spring. There is no compression which is happening into the spring right now at this stage. So, and G is given 10 meter per second square. So the question here that if I want to place some mass here, let's say I'm putting up M mass, and this value of M we have to find out, for which this wooden block will not completely submerge in the water. So basically, when you will be placing this mass, this block will be going down. So you have to calculate the value of M for which this end, basically water will not come to the upper surface. We have to calculate that value of M. So I think the question is, you understood the question. Now we'll start solving it. So before putting the mass, let's first get this mass outside. So when this block is floating, at that time, some portion of the block will be outside. I'm calling this as X. So it was floating. So I have to calculate first this value of X. So to calculate the value of X, we have to make the FBD of the block. So wooden block. We'll make the FBD will show all the forces. Since it is in equilibrium, it is floating, so acceleration has to be 0. So buoyant force will be acting in upward direction onto this block. There will be this mg which will be acting downward. And since this spring is just touching it, there is no force applied by the spring. There is no compression in the spring. So I will not show any force corresponding to spring here. So these two forces are acting onto the block, and the block is in equilibrium. So we have to calculate the value of X. So if we calculate the value of mg, the value of mg will come out to be the volume, which is 3 into 10 to the power minus 3 cube, multiplied with density of the block, which is 800, multiplied with g. That is the weight. So volume multiplied with density multiplied with g, that becomes the weight of this block. Now we have to calculate the buoyant force. So you see, buoyant force by definition is equivalent to the weight of displaced liquid. So the displaced liquid, if you see, this block will be displaced in the liquid corresponding to that much of volume, which is inside. So this total is 3 centimeter. This is X. So this value, if you will calculate, that will be 3 minus X centimeter. So the buoyant force will be equals to A square, because, sorry, it is 2, not 3. It is in centimeters. So A square multiplied by this dimension, we have to take 3 minus X into 10 to the power minus 2, multiplied with 1000, because it's the weight of this is the buoyant force we are taking. So we have to consider the weight of fluid there. So if we equate these two forces, this will cancel out. So the remaining will be 3 into 10 to the power minus 2 multiplied with 800, and that will be equals to 3 minus X multiplied with 10 to the power minus 2 multiplied with 1000. So if we rearrange this thing, so 24 is equals to 30 minus 10x. So 10x becomes 6. So x becomes, if you see this, it becomes 0.6. centimeters. So that much portion is above the water level. Now, this is a case for flotation, meaning this wood is floating right now. Now, what we have to do, we have to place some extra mass onto this wooden block so that that much portion should also go inside. So, we'll go for the second case. And we'll make the FPD for that also. So, if we make the FPD for the second case, when we have placed the point mass, So after placing the point mass, we'll make the FBD. So mg is still acting downward. There is this buoyant force, but this time the buoyant force will be more because this will be coming down, and there will be some m dash g, and acceleration should still be 0. But you see, when this block will be going down, there will be some compression which will be happening into the spring. So corresponding to that compression, a spring force will also come into effect. So if you one by one, if you calculate the value, so fb dash, since whole block will be going down, so fb dash will be equivalent to the total volume of the block, which is 3 into 10 to the power minus 2 q multiplied with the density of the fluid, that is 10 to the power 3 multiplied with g. The kx, the value of k is given, that is 50, multiplied with the value of x. So you see, this block will be going down by this amount. So you multiply that. Obviously, we have to convert that in meters. So it will be 0.6 into 10 to the power minus 2 Newton. Then this mg is not changing. It is similar to the previous case. So value of mg will be 3 into 10 to the power minus 2. The cube of that multiplied with 800 into g. And m dash g, that value we have to calculate. We put that in equation. So m dash g plus mg, which is 3 into 10 to the power minus 2 cube into 800 g, that will be equals to 3 into 10 to the power minus 2 cube into 10 to the power 3 g plus 50 into 0.6 into 10 to the power minus 2. So if you solve this equation, the value of m dash, when you solve this whole value, the value of m dash will come out to be 0.035 kg if you do the calculation. That much is the value. So the thing is, when there is no spring and when there is no point mass, this wooden block was floating. And when it was floating, some of the portion was above the water, some was below the water. And there was this spring which was just there. It was in the natural state. So we had to calculate the value of m dash, for which this block should be going down, but not completely. It has to go down so that its upper surface should be touching the water. That was the equation, and when we calculated the value of m dash, that value came out to be 0.035 kg. That much point mass you have to place onto the wooden block to get the desired result.